Mass on a spring. Before we talked about mass on a spring with regard to thinking about the work done to compress or stretch a spring. But now we're going to be thinking about the motion and trying to model that motion. So we've got a wall here. We've got some ice down here. We've got a vacuum chamber that all this setup is in. And we got a mass attached to a spring attached to the wall, a block here. And we're interested in knowing what happens if we take this mass and stretch it and either maybe let it go from rest, or maybe we hit it with a hammer or something like that. This way, or maybe even this way. What happens? What is the motion like? Do notice by having ice in a vacuum, I'm trying to minimize friction. But even when you do that, there's still friction, right? The spring's got friction. The molecules in the spring are rubbing against each other. Right, do molecules really rub? Well, okay. There are electric forces in there that are sort of rubbing. It does cause friction. You can't get rid of friction. Okay. Pretend there's no friction in the spring either. It's a frictionless spring. What do we want to do? We want to model the motion. Let's call the horizontal axis X. X is going to be the position of the mass. I drew it like this, but that doesn't mean it's necessarily at equilibrium. The equilibrium position could be somewhere else, maybe there. That could be your equilibrium position. And that would make sense to call it X equals 0. So if the mass is further to the right, the spring is stretched. That means X is positive. On the other hand, if you push the spring, compress it toward the wall, past the equilibrium position, X would become negative. You'd want the sign plus or minus to be taken into account. We do use, as with free fall, Newton's second law, F equals ma, to get our differential equation. In physics, often called the equation of motion. F equals ma. For this situation, the force is the force due to friction. You could call it F sub friction if you like. With up and down motion of a mass under gravity and air resistance, the frictional force, I think I labeled F sub air for air resistance. You could call it F sub resistance as well. Equals the mass times the acceleration. The acceleration is dv dt, the derivative of v with respect to t. But I'm not going to leave it as dv dt because the friction force by Hooke's law is negative k times x for some constant k. That's Hooke's law. Hooke's law says the friction force is that. Oh, I said this wrong. It's not a frictional force. I'm pretending there's no friction. Sorry, this is F sub spring. It's the force due to the restoring force of the spring. Oh, that was a bad mistake. No friction, right? Pretending there's no friction. Pull that mass to the right, make X positive. The restoring force is in the opposite direction, negative. It wants to, you got to pull it harder and harder to go further and further. Compress it so that X becomes negative, the restoring force is in the positive direction. It has the opposite sign as X. So there's a constant of proportionality, K, or negative K, where the spring force is negative Kx. Is that really correct? It's not perfect. Okay. You might say Newton's second law is as close to perfect as it gets, F equals ma. But the force itself, described as negative Kx, is not perfect. It's pretty good for small oscillations. But if you go extreme, you pull the spring too far, it's going to break. So for sure, it's not good there. Or even if you compress it to the wall, it could break. Even if you don't push it to the breaking point, it still maybe is not so good eventually, but it's simple and we like simple. We also write the derivative as the second derivative of the x with respect to t twice, instead of the first derivative. Why? Because we want our differential equation to involve the unknown function x for the position. We do want to solve for the position x as a function of t. If we wanted to know the velocity, we would just differentiate x. Find dx dt, and that would be v. There are various equivalent ways to write this. One equivalent way to write it is to, for example, divide both sides by negative k, or maybe just k itself, and write it as m over k times the second derivative equals negative x. A more common way to do that is actually divide both sides by m and write the second derivative of x with respect to t as negative k over m times x. That's a more common way to write it. One last way to write it is to then add k over m times x to both sides and write it in such a way that you get 0 on one side. Any of these ways of writing this differential equation is fine. Though as far as finding solutions, this is probably the easiest form to think about. Remember, you want to imagine the differential equation is talking to you. It's saying, hey, you, find me a function x of t whose second derivative is a negative constant times itself. If k over m were 1, it would be negative of itself. Cosine or sine have second derivatives that are the opposites of themselves. Got this extra complicating factor of negative k over m in there. But still a little bit of guesswork would reveal that x equals cosine of square root of k over m times t, and x equals sine of square root of k over m times t are solutions. Should be able to check that. You do it with the cosine. Let's check. And I'll do it with this form of the differential equation. So what's the left-hand side? It is the second derivative of x with respect to t twice. So I need to find the first derivative first. That's going to be negative sine of square root of k over m times t times, don't forget, chain rule would give you an extra factor of square root of k over m, right? Because the derivative of the inside function, constant times t, is the constant. It's a complicated constant, but it is still a constant. Then when you differentiate that, the derivative of sine is cosine. The derivative of negative sine is negative cosine. This square root of m stays there, but we also get another factor of square root of k over m from applying the chain rule twice. We use the chain rule in both circumstances here to get that and to get this. Simplify a little bit. Square root of k over m times itself is k over m. So we get negative k over m times cosine of square root of k over m t. And that is, lo and behold, negative k over m times x. Why? Because that equals x. There it is. For this function that I'm checking. And this is true, we get equality for all t. You see a t there, you don't see a t there. Okay, it's in your mind. X is a function of t. Imagine it to be there. And that is the right-hand side of the differential equation in this form, negative k over m times x. I could do a similar checking with sine of square root of k over m times t. I won't. Instead, what I'll do is I'll write down a general solution, and I'll also solve an initial value problem. So a general solution turns out to be an arbitrary constant, call it C1 times the cosine solution, cosine of square root of k over m times t, plus another arbitrary constant, C2, times sine of square root of k over m times t. That's a general solution of the differential equation, the second order differential equation involving a second derivative of an unknown function. Makes intuitive sense that we're oscillating back and forth the mass on the spring with constant amplitude if there's no friction, if there truly is no friction. But what if we have an initial value problem? And a typical kind of initial value problem might have x of 0 being some positive number like 1, just to pick something particular. This would be 1 meter. And initial velocity equal to 0 meters per second, say. In other words, we're stretching the mass 1 meter to the right. Okay, it's a very big spring. We can stretch it 1 meter to the right, and we're letting it go from rest. That's our initial value problem. We like to find the unique solution of this. Before I do so, I probably should mention something about units for K in particular. I will go back to that sheet, but coming back here, I should emphasize, since these things are forces, they are newtons. X is a position in meters. In order for the product of these things to be in newtons, K would have to be in newtons per meter. The spring constant, K, that's what it's called, the spring constant. It's a measure of how stiff the spring is in newtons per meter. The bigger K is, the stiffer the spring is. The stronger the restoring force is, the harder it is to pull. The smaller K is, like a slinky, the easier it is to pull. But its units are newtons per meter to make the product have a units of newtons. All right, how to solve. Use the general solution, use the initial condition to solve. Question?
Yes.
No, I made a mistake. That should be a second derivative. Couple mistakes today. If this is x of 0, plug in t equals 0, get c1 cos 0 plus c2 sine 0. Cos of 0 is 1, sine of 0 is 0. This simplifies to c1. C1 is 1. That's nice. What about C2? Take the derivative. X prime with respect to t. You don't forget about the chain rule. Here you'll get negative C1 square root of k over m sine square root of k over m times t. Here you'll get plus C2 square root of k over m sine, or take the derivative, cosine of square root of k over m times t. Now plug in t equals 0 and set the result equal to 0. Negative C1 square root of k over m times 0 plus C2 square root of k over m times 1, cosine of 0 is 1, simplifies to C2 square root of k over m. That's equal to 0. The only way that's going to happen is if C2 is 0. If the initial velocity were not 0, like if we hit it with a hammer in one direction or the other, then the C2 would not necessarily be 0. In fact, it would not be 0. By the way, when you hit with a hammer, you don't have to worry about, the minuscule amount of time as the hammer is impacting the mass. Okay, it's just too complicated to worry about. Keep it simple. Just assume that the initial velocity is something non-zero. Once we've got these constants, the unique solution of the IVP is x equals C1 was 1, 1 times cosine of square root of k over m times t. And C2 was 0. That's it. That's done. That is the one function that solves the initial value problem. What does its graph look like? Its graph looks like this. Of interest is the amplitude and the period. The amplitude's simple, it's 1, though if you had both cosine and sine, the amplitude gets more complicated. The period's fairly simple to figure out as well, though, even if you had a sine in there. Period t can be found but from the formula as 2 pi over the coefficient of t there, square root of k over m. And the more common way to write that is 2 pi times the square root of m over k. You've probably seen that formula before. That is the formula for the period in terms of the mass and the spring constant. If you keep the spring the same, so k is the same, but increase the mass, it predicts a bigger period, slower motion. That makes sense. If the mass is humongous, yeah, it's good. The spring's going to have a hard time moving, you might say. On the other hand, if the mass stays the same, but you change the spring and make it a stiffer spring, k gets bigger, that makes t smaller. That's a faster oscillation. Yeah, it's a real stiff spring, it's a real strong restoring force. That corresponds to a faster oscillation. What if there's friction? With friction, no vacuum anymore, no ice. F equals ma becomes, now we do have a friction force, but also the spring restoring force. The acceleration is still the second derivative with respect to time. As before, the spring force is negative kx. What about the friction force? It's a negative constant. I'll call it negative b times the velocity. Just like with air resistance for a falling object. Call the constant negative b, often called the damping constant. It gets multiplied by dx dt. Yeah, that is the same as v, but I will, in the differential equation, leave it as dx dt. This is also a second order equation. It's common to rewrite it by getting everything except 0 on one side and also dividing everything by m. So you most commonly would write it like this. I rearranged and divided everything by m. Let's take a particular case with particular numbers. Let's pretend m is 1 kilogram, b is 7. Its units would be newtons per meter per second because it gets multiplied by v to get a force. And k, let's take to be 12 newtons per meter. So we get, if we do that, I'll write prime notation to save some time here. X double prime plus 7x prime plus 12x equals 0. What kind of guessing could we do here? You could try guessing a cosine and sine again, but if you do, it would not work. A plain cosine or sine here does not work. There's some friction. What's going to happen? It could oscillate with a smaller and smaller amplitude till it eventually essentially comes to rest. Or if this friction really is high enough, like it's sitting inside a tub of molasses or something, that might be friction so large that maybe it doesn't oscillate at all. You pull it away from equilibrium, it slowly moves back to equilibrium without oscillating. In general, when you have an equation like this, a second order scalar differential equation with constant coefficients and it's no external forcing is what the 0 represents, it's best to guess, maybe somewhat counterintuitively, an exponential function, say x equals e to the rt for some unknown constant r. That turns out to be the best guess. as we will see here. If you think about it, R should be negative because X should decay to 0, not grow to infinity. So the R should be negative, but how do we figure out what the R is? If we assume this function works, we should take its derivatives with respect to t and see if we can solve for R by substitution. Now substitute all those things into the differential equation. Replace x double prime with r squared e to the rt. Replace 7 times x prime with 7r e to the rt. And replace 12x with 12 e to the rt. Set this equal to the right-hand side. You're hoping you can make this true for all t. Doesn't look like it's possible. But it is if you factor out a common factor of e to the rt, which is never 0. This is never 0. And therefore, the coefficient must be 0. And look, lo and behold, you get a quadratic equation that we could solve for R either by factoring or with the quadratic formula. That's a 12 there. In this case, we can factor as R plus 3 times R plus 4. So it looks like two values of R that might work are -3 and -4. What we've really done, logically speaking, is we verified that if this kind of function is a solution, the only way that's going to happen is if R is -3 or -4. We've technically not verified that -3 and -4 truly do work, though you can check it, they do. Effectively, this logic is reversible. These things have names. This is called the characteristic equation. Characteristic equation. And these numbers, 3 and -4, are called the, wait for it, the eigenvalues. Eigen is a German word. Don't say eigen. Say eigen. EI in German sounds like an I. IE sounds like an E. EI sounds like an I. Eigenvalues. Eigen basically means characteristic. So we could call them the characteristic values, but it's more fun to say eigenvalues. I mean, you could call that an eigenequation too, but for some reason, traditionally, we don't call it an eigenequation. It turns out because of this, y equals e to the -3t and y equals e to the -4t are solutions, though that does take checking to prove it. And a general solution turns out to be a linear combination of those, an arbitrary constant times e to the -3t plus another arbitrary constant times e to the -4t. Just like the previous example was a linear combination of cosine and sine. These are also linear algebra topics. We say these two functions form what's called a basis for the solution space. They span the solution space. Every solution is a linear combination of them like this. And they turn out to be what are called linearly independent functions. They're not, with two of them, they're not scalar multiples of each other. This general solution allows you to solve any initial value problem that you want. I'm not going to bother doing so. You could do it. Very similar to what we did with the cosine and sine example. But this is a pure cosine and sine with no decay. This is pure decay. Is there something in between? Yes, there is. You can have a small amount of friction that gives you some oscillation, but the amplitude decays to 0. It's like an exponential decay times a cosine or a sine. And to derive what such functions are, the best way to do it is with complex numbers. There are some differential equations where the coefficient of damping is fairly small, and when you do this guessing and solve for R, the eigenvalues, you get complex number eigenvalues. And It turns out that when you get complex number eigenvalues, you end up using the fact that e to the it is cos t plus I sine t, where I is the imaginary unit, to help you ultimately figure out what the real solution is. It's amazing. I'm not going to show you details. You'll learn that whether you take Diffie-Q with linear algebra or just plain Diffie-Q. Complex numbers are useful here. And they do more than just help you solve the equation. They give you more information, amazingly, beyond just the solution itself. You can pretty much find the amplitude and phase shift of the solution more easily with complex numbers.